show that I actually went 10 feet in distance. Actually, it would be 15 feet, wouldn't it? Because I'd go out 5, come back 5, and I'd go 5 more here. Okay, so the actual distance traveled would be 15. So they're different. Displacement is different than distance traveled. Okay, so that's what displacement is. It's basically where you end up relative to where you start. Right? So let's say we have a function representing displacement. In math, a lot of times we represent displacement with a function of s of t. And sometimes we actually call it position instead of displacement. An object's position as a function of time. So t is the time. In physics, a lot of times you'll call displacement x of t. Just a little bit different notation. So if we do the derivative of displacement, s prime of t, well, that's basically what velocity is. Now, velocity could actually be negative or positive. Velocity is also directional. It's a vector. It has a quantity and also a direction. So we will say, at least for right now, in a simple situation, if we're analyzing the velocity of an object, positive velocity means we go to the right, and negative velocity means we go to the left. Or if it's more of a vertical motion, let's say positive velocity is up, negative velocity is down. Okay. So velocity is directional. Now we can actually think about the second derivative. So second derivative is actually called acceleration. Okay, so the rate of change of displacement is velocity. The rate of change of velocity is acceleration. Okay. A lot of times we'll actually refer to the velocity function as v of t, and the acceleration function as a of t. And in that case, acceleration would also be v prime of t, the derivative of velocity. Okay? But that's just some basic definitions. Okay? Now you might wonder where does speed fit into all of this? Because that's probably, when you first learned about how fast something goes, you called it speed. Well, speed, the definition for speed, is the absolute value of velocity. Okay. Speed is what we call a scalar quantity. It doesn't have a direction associated with it. It's just literally how fast are you going with no attention paid to direction. Whereas velocity is directional. So that's the difference. So speed is always positive. So it's the absolute value of velocity. Okay. All right, I want to have you guys look at a problem real quick here. Okay, so on the screen here, you see a picture of the displacement of a function. We'll just call it f of t. And this doesn't even have units, but let's say this represents the displacement of a particle moving left and right on a numbered line. Okay, so it's going left and right. So this is a graph of the displacement. So notice sometimes the displacement's positive, sometimes the displacement's negative, but this graph and this function should tell you, kind of give you a picture of the motion of the particle. It's basically where on the number line is the particle at each of these times. So the t-axis, the x-axis are times, and let's say that those are in, say they're in seconds. And then the y-coordinate is the number of, let's say it's feet, that you are from the where you start. Okay. So at the starting point, notice at t equals 0, the position is 0. So this particle starts at the origin. Okay. At this other time, let's say t equals 4, the particle looks like it's at about negative 1.5, which means we're 1.5 units left of the origin. That's where we would be on the number line. So that's how to interpret this graph. Now what I want you guys to do before we go over these answers is to think about these questions that I have written on here. First question is, using this graph, when is the particle moving left and when is it moving right? And when would it be stopped? And how would you answer that with a graph? When is it going to the fastest? In what direction is it going the fastest? And then the last question is, when is the particle farthest away from the origin? Okay, so I'd like you guys to take a couple minutes, talk it over with the people at your group. If I could have the substitute pause the video for a little bit, I'll come back with the solution in just a second. Okay? So work on this problem, and come back with the answer momentarily. Okay, so let's discuss the answer to this. When is the particle moving left? Well, the particle is going to be moving left whenever the rate of change is negative. Okay, so if this is the displacement function, when it's moving left is when the velocity would be negative. Velocity is rate of change of your position or of your displacement. So places where we would be moving left are right here, in this particular section, so that's between 1.5 and 3. In this particular section, between 4 and 5, we have a negative slope, and that's it. So those are the places where the particle would be moving left. Where is it moving right? Well, it's going to be moving right whenever the displacement has a rate of change that's positive, okay, or the slope is positive. So between 0 and 1, it's going to be moving to the right, which is kind of obvious. You start at 0 and you end up at 1. And then you're also going to be moving to the right between 3 and 4 seconds, and between 5 and 9 seconds in this whole area right here, because the slope is positive. Okay? So you got to think about looking at slopes when you're thinking about velocity. And the thing we got to get tied up with is that you see down here the graph is negative, so you think negative values, but the displacement is what's negative. We're answering questions about velocity. We have to think about the slope of the displacement graph. When's the particle stopped? The particle will be stopped when the velocity is 0, or the rate of change is 0. So that's going to be on these sections where the graph goes flat. So right here, and on this interval right here. And that kind of makes sense because in this whole time interval, in this half a second time interval, you can see that the displacement doesn't change. If the displacement doesn't change, that means the particle's not moving. Okay, so when is it going the fastest? Well, that's when we will have the highest velocity, and so that's going to be when the graph is the steepest. And so if you kind of analyze the slopes, I think we're probably tied, unless you actually calculate it here. Here we've got a slope, and this slope, they're pretty close. This slope is 1, and let's see here. We go up 2, over 2, this slope is also 1. So that would be when it's moving the fastest. Now we also want to consider negative. That's when it'll be moving fastest to the right. We also have to consider negative slopes. Like in this particular section here, it's a run of 1 and a rise of 1, 2, 3. So in this particular section right here, the speed is actually 3. Okay, the velocity is negative 3 because that's the slope right here. So this, I guess, would be the answer for when it's going to the fastest. So whenever the graph is the steepest, whether it's up or down, increasing or decreasing. Okay, and then as it says, in what direction is that? Well, that's to the left, since the velocity is negative. Okay, last question. When is the particle farthest away from the origin? Well, it's going to be farthest away from the origin when it has its maximum displacement. Okay, so notice that on the maximum displacement on the left is 2 units, because we're negative 2. So we're actually looking at function values here, not slopes. And then on the other side, like between 9 and 10 seconds, we're out about, looks like about 2 units away. So 2 units is the furthest we get from the origin. Okay? All right, so now I'm going to consider this graph again. But now let's assume that this graph doesn't represent position anymore. Okay? Let's say that it represents velocity. If I can get this to work. Seemed easier than it is. All right. The same graph